about problem 3. Yeah, problem 3 is kind of fun. Um, yeah, yeah. So in this problem, yeah, like he has an index J, and then he has AJ written on it, and then basically he's allowed to cyclically shift the elements by 1, and then write down the value. Um, then he wants to find the minimum number of operations um, uh, to so that the total number of distinct integers is equal to the distinct integers in the array, right? And you need to output that for every starting index, right? So I think yeah, one thing to it's a bit weird to think about cyclically shifting things. Um, but you can you don't have to think of the array as circular. You can just think of it as a linear array if you make like multiple copies of it, right? So I'll just draw for this example. 1, 2, 3, 1, 3, 4, right? So let's just make multiple copies. 1, 2, 3, 1, 3, 4. And then 1, 2, 3, 1, 3, 4. And then 1, 2, 3, 1, 3, 4, right? And then this problem reduces to being like for each index over here, you want to find like you can either go to the left or to the right, and you want to find the minimum number of moves you have to make such that you see all the distinct elements, right? Yeah. Um, yeah. So I think one thing that like you can kind of see, like one thing that can be noticed is like if you fix a left endpoint and you decide to only go right until you see all the distinct elements, the places where you see the distinct elements is something you can find via 2 pointers, right? So I'll just demonstrate, right? Let's start over here, right? So you have to go all the way here to see all the distinct elements, right? So you can do 2 pointers where you maintain like a map of the frequencies, and then you just like erase from your map if the frequencies ever 0, right? So if this is your left endpoint, then you can iterate all the way here. And this is the first time the number of distinct elements will be 4. And then you just increment this, and then the right endpoint still stays the same, right? And then I'll use another color. You increment this, the 2 goes away now, right? So you have to like keep moving the right endpoint until the number of distinct elements is back to 4, right? Yeah, so basically you can do 2 pointers like to find for each index how many times I need to go right before I see all the distinct elements, right? And then you can also do 2 pointers from the right to see from the right how many spaces left I need to go to see all the distinct elements, right? Yeah, so like for special cases, maybe like the strategy is for Farmer John to keep cyclically shifting right or keep cyclically shifting left, right? So yeah, we can just like pre-compute. So um, yeah, so this is, I mean, I'm not saying the solution yet, but these are just like helpful things to observe, right? Um, like if Farmer John decides to go like keep going left or keep going right, yeah, uh, you, you can calculate this using 2 pointers in a map. So number of steps left from I to see everything. And then right I, we can define it to be number of steps right from I, right? Yeah. So, okay, so let's go back to the original problem, right? So it's asking for each I, uh, how many steps do you need to take to see everything, right? So let's consider what like the things we see actually looks like. So let's say this is index I, right? So we're gonna see, of course, we're gonna see what's at index I, and then we might also see things to the right of it, and then we might also see things to the left of it, right? So maybe in our path, we end up visiting these indices, right? And given an interval, the shortest way to like actually visit it is either you go to the right side and then you go all the way to the left, or you go to the left side and then you go all the way to the right, right? Okay, so let me just draw it again below. So let's say this is index I. This is index I, and there are two kinds of paths that you might make. One kind of path first goes to the left and then goes to the right. So this is like case one. And then the second kind of path goes to the right and then goes to the left, right? This is case two, right? Let's focus on case one, right? Yeah, so let me repeat what we just did, or like how we're viewing this problem, right? Or I guess like one thing we observed earlier is you can use two pointers to see like if you only went left, um, how many how many moves you need to make, and then if you only went right, how many moves you need to make. And otherwise, there's two kinds of like ways you'll move, right? Since when you move, you're going to visit an interval. Either you go to the left and then you go to the right a bunch, or you go to the right and then you go left, right? So let's consider case one, right? So I'll just draw it again here. So let's like focus on case one. We're at index I, and then we go to the left, and then we go to the right, right? Um, and like technically when we go to the left, the amount we go to the right, we we only need to go enough to see all the distinct elements, right? So the length of this, so if this is equal to j, let's say we go left from I to j, the length is equal to right of j, right? So technically for each index I, we want to maximize or minimize over j less than I of the length to go to I from I to j plus the length to go right from j. So it's going to be I minus j, sorry, I minus j plus right j, right? Let's like rewrite this a tiny bit. So we can pull the I out. So it's going to be, yeah, so I plus min over j less than I of right j minus j, right? Right? And there's something special about this. This is just a prefix min, right? So technically this is a prefix, like assuming we already calculated left and right, the answer just like this index, the answer for this index is just the index plus a prefix min of right j plus minus j, right? Uh, yeah, so we already know how to calculate left and right. You just do that with two pointers, and then you just do a prefix min of this value over here. So you consider right j minus j for every index, and then you can just pre-compute the prefix min. So for this case where you start going left and go right, the answer is the index plus a prefix min of right j minus j, right? And I think, yeah, you can also argue similarly for the other case. If you're at I, and then you go to the right and then back, this is going to be min over j greater than I of j minus I plus left j. So this is going to be like negative I plus min j greater than I, j plus left j, right? Yeah, so this thing over here is a suffix min. Sorry, not everything, just this part, suffix min. Yeah. Yeah, so this problem ends up being like two pointers and prefix, suffix, min. Any questions? Yeah, I think when I originally tried this problem, I kind of like I came up with the wrong solution because I assumed like only the left eye would matter, and like maybe you just go from I to here and then here. But yeah, so there are some cases where you have to start going right and then go left. Um, yeah. Or I think my original idea was like for all these intervals in your two pointers, consider the smallest one that contains I and then calculate for that. But that doesn't quite work. Yeah, but this thing works, right? You can provably like there will be some interval that you visit, and then there's two ways you can visit the whole interval. Either you start right and go left, or you start left and go right, right? And then if you consider each case, it simplifies quite nicely, right? So if you start left and then go right, yeah, so you can write it as some kind of suffix min, right? Yeah. But yeah, I think like to solve this problem, it's like, yeah, yeah, I think it's pretty helpful to like know that these are things you can compute. Like given a position, where's the rightmost place I could go so that there's that many distinct elements. And so you can use two pointers to the map. So I guess this kind of thing comes up a lot in problems. Yeah, but any questions about this problem? Okay. Yeah, I'll take any questions you'll have. Yeah. Any general questions about the contest or any tips and tricks, anything. But yeah, in case yeah, anyone didn't see, yeah, or I'll just like recap. Yeah, so the first problem was yeah, kind of a constructive problem. Yeah, I guess more constructive than greedy. Um, yeah, uh, or like you had to like understand the structure of uh like like whether like how like when two cows are the same or different, how that changes things. Yeah, and then this one was just like you make one observation and then you have to like think very carefully about how to implement it. Yeah, and this one is a nice problem that you can do with two pointers and prefix uh, max/min. Yeah, yeah, thanks. Yeah, I'll take any questions.
Yes, thanks, Arvind. Just I mentioned before, Arvind is our silver level coach. So welcome to take any silver level question to Arvind. Because SCAM not only focus on the algorithm teaching, but also coaching. We do the customized coaching to every student. Yeah.
Yeah, I think one other comment I'll make is like, yeah, I think a lot of silver problems, they're actually like pretty similar to problems you'll see on Code Forces contests. At least the like greedy and ad hoc problems. Like probably like problem two, I don't think I would find this in a Code Forces contest. It's probably like too implementation heavy. But I think the style of the problems for problem one, where you have to make that construction, and then problem two, where you reduce something to like two pointers, prefix, suffix, maximum. These are also like pretty fair game for Code Forces contests. So I think like if you do Code Forces contests, that can also like give you very good practice for this kind of stuff. Yeah, I think, yeah, I actually started doing contests in college. I never did USACO, but yeah, when I used to do contest, I think like doing code forces and and the rating was a motivator. And I also had like other friends who did these contests. Oh, sorry, I didn't read the chat. Oh, okay.